Okay, so does anybody still remember what we were doing before the exam?
Cauchy sequences.
Cauchy sequences, yes, yes. So we are trying to answer in a slightly different way, what's special about R, right? And so we have these two notions that we introduced right at the end. One is Cauchy sequences, and the other is diameter. Okay. So does anybody remember what a Cauchy sequence is? So you have some sequence, right? Sequence is called Cauchy, right? Called a Cauchy sequence. If something happens, right? So what kind of thing has to happen? Right? Or can anybody give just sort of like a, maybe not the, you can either give the actual rigorous definition, or you can give some sort of hand wavy, like feely, touchy-feely definition of what a Cauchy sequence is. Either one is good. Yeah, Charlotte.
For all epsilon greater than 0, there's an integer n such that past that n and an m past that n, the distance between p sub n and p sub m is less than epsilon.
Right. So given any epsilon, there exists a time. Exists a time, and this time has the property that if you're past that, if n and m are past that time, then the distance between the 2 points is smaller than epsilon, right? So, in other words, you can make the distances between your points as small as you want. You can make elements of the sequence as close together as you want, right? So that's a little bit different from convergence, right? Convergence means that, right, if we say Pn converges to P, right, then that's, given any epsilon greater than 0, there exists an n, there exists a time such that if, any point past that time is within epsilon of that point. Right? So you can make everybody as close to this point as you want, right? You can make everybody as close to that point as you want. Here you can say you can make everybody as close to each other as you want. Okay, so it's slightly different. Right, so this is just plain old convergence. Right, just a plain old convergent sequence. And this is a Cauchy sequence. Okay, and then there was this other notion that we introduced, the notion of diameter of a set, right? So you have some set that's a subset of X. The diameter of the set was defined as, anybody remember that? How you get the diameter of a set? What's that? N?
Is it the maximum, the supremum of the distances between the points?
Exactly. So what you do is you construct the set of all distances. So you say, let's look at the set of all distances between points. Right? Let's look at all distances. Let's take all pairs of points in that set, and then look at all distances look at all possible distances, pairwise distances, right? That, and then take the supremum of that. Okay. Right. Okay. And the one thing that we remarked at the very end was that if you have a sequence, Pn a sequence, and if we let E sub n denote all terms from P sub n onwards, right? So this is what we call a tail of the sequence, right? So let E sub n be defined as the tail from this point onwards. Then we observe that the sequence is Cauchy if and only if the diameters of the E sub n go to 0. Okay, and I hope that's I'm not gonna prove it. I'll let you prove it if you want to. I hope that's at least intuitive, right? Because the diameters are if you can make the diameters as small as you want, that means that you can make the tail as small as you want, right? If you can make the tail as small as you want, that means that everybody past a certain point is as close together as you feel like, and that's what Cauchiness is, right? Cauchiness means you can make everybody as close together as you want, right? Given control of the time when you start looking at them. Okay, so that's where we finished. I guess I wasn't going to do it in this order, but since we have Cauchy sequence and convergent sequence up here, which one is stronger? Right? Is it stronger to be a Cauchy sequence, or is it stronger to be? Is it more restrictive to be a Cauchy sequence, or is it more restrictive to be a convergent sequence? In other words, is this one stronger than that one, or is that one stronger than this one, or maybe are they equivalent to each other? Right. Which one is it? Is it this way? Is it option number 1? Convergence is stronger than being Cauchy, or option number 2, Cauchy is stronger than being convergent. Turn to a neighbor, talk to somebody nearby.
Because of your past distance.
I think so. That's convergence.
What do you think is
If you like fix the points, you would like get convergent.
Okay, we're gonna vote. Who thinks that it's 1? Convergent implies Cauchy. Who thinks it's 2? Cauchy implies convergent. It's actually this way. Convergent implies Cauchy. So let me give you an example of a Cauchy sequence that does not converge. Okay, so here's a counterexample to 2. Right, so counter. Consider, let your space be, say, 0, infinity. Okay, with the standard metric. Okay, and let your sequence be p sub n. Let p sub n be 1 over n. Okay, so this is a Cauchy sequence because you can make these guys as close to each other as you desire, but it doesn't converge, right? Because there's nothing for it to converge to, right? There is no point that this sequence converges to. Okay, does that make sense? Right? If 0 were in here, then it would be a convergent sequence, but there is no 0 here for it to converge to, so it actually doesn't converge. Okay, so yeah, so you might so Cauchiness. This is Cauchy, but not convergent. Okay. Okay. Let's show that convergent actually implies Cauchy. Right? Does that seem reasonable? I guess maybe it doesn't seem reasonable. Nobody voted for it. But think of what convergent means. Convergent means that there's some point, and given any epsilon, you can make it so that everybody, you can find a time past which everybody's inside that neighborhood, right? So there's some time, and then past that time, everybody's inside here, right? Well, for Cauchiness, we want everybody to be close to each other, right? We want to find a time such that everybody's close to each other. Well, is everybody close to each other? Yeah, right? So convergent, you can sort of see that convergence should imply Cauchiness, right? How close is everybody to each other? what's the farthest they could be? The radius is epsilon here. What's the farthest that they could be from each other? 2 epsilon, right? Right? The farthest you could be is like 2 epsilon, like if you're at both edges of the ball, right? And you can see that 2 epsilon by using the triangle inequality, right? Because the distance of, if you take any 2 points, Pn and Pm, well, it's hard to say anything about the distance between them, but I do know that the distance between each of them and P is bounded by epsilon. So triangle inequality tells you that their total distance is bounded by 2 epsilon, right? So if I want to make these guys within epsilon of each other, I just choose a smaller ball, right? I'll choose the epsilon over 2 ball, and then everybody will be within epsilon of each other. So that's the proof. So, well, right? Suppose Pn converges to P, right? So we want to show that, given epsilon, there exists a time past which the distance between Pn and Pm is smaller than epsilon, right? And by past which, of course, I mean such that if n and m are bigger than the time, then you have this. Okay. Well, somebody gives you an epsilon. Given epsilon, we know, since Pn converges to P, we know that there exists a time past which the distance from Pn to P is smaller than epsilon over 2. Right? We do know that there's a time past which everybody's, within epsilon over 2 of P. Right? Right? And so, thus, if n and m are greater than n, then the distance from Pn to Pm is controlled by the distance from Pn to P plus the distance from P to Pm, which is smaller than epsilon over 2 plus epsilon over 2. Okay, so there's kind of 2 parts to how you do this sort of stuff. One is have an intuitive idea of what's going on, of what everything means. One, like, what does convergence mean? Well, it means that we can get things close to P, right? What does Cauchy mean? It means we can get things close to each other, right? And so you think about it, you imagine it, and you think, oh, look, if I can get everybody close to P, that means they're close to each other, right? And then you start, so the idea is sound. Right? And then you think, okay, what exactly do I need to do to prove this rigorously? Right? To prove this rigorously, I need to show that given an epsilon, I can find a time past which everybody's within epsilon of each other. Right? That's how you do it. Okay. Okay. Any questions? Okay. Okay, so let's come back over here, and we're going to say a little bit about the notion of diameter. Yeah. Yeah. Okay, yeah, we're going to say a little bit about the notion of diameter. This is why I should never change the order of my presentation. So, not sure which is the right way to go now. Lost. Okay, so here's the first thing we're going to prove, just like an observation. I think it's called a theorem in the book, but it's kind of a minor theorem. So the diameter of the closure of the set is somehow related to the diameter of the set itself. That's another theorem, of course. What should this be? What do people think about this? The relationship between the closure of the set and the set itself. You're taking the diameters, like the distances between 2 points you take distance between 2 points in the closure, 2 points in the original set, and you take the supremum of all those distances, supremum of all these distances. What do you think? What should the relation be?
Greater than or equal?
Greater than or equal. So that's for sure, right? Because you've got more points over here, right? This guy has more points, right? Right. You're throwing in more points. You're throwing in the limit points. Yeah. So that is kind of like immediately true, right? And
Oh, is it equal?
it's actually equal. Yeah. So the theorem is that in fact the other direction also holds, right? That and which forces them to be equal to each other. That. So why do you think that? Why does that make sense? Right, you've got your set. Right, you've got your set, and then you've got the closure of the set, right? Which means that you throw in any points where you've got limit points, right? So you throw in limit points, right? So should that change the diameter of the set? Not really, right? Because the limit points, you can get infinitely close to any limit point with remember what the limit point is, right? Every punctured neighborhood contains somebody in the set, right? Contains somebody in the set. So no matter how close I demand, there's always going to be somebody in the set, within that, that close to that point. I can get points infinitely close to that limit point. So throwing those guys in won't change the diameter, right? That's the idea. Okay. So you say, well, look, proof. Choose 2 points. Call them P and Q. Yeah. So choose any 2 points, P and Q, in the closure. Okay. They're either in the set itself or they're limit points, right? So they're either in the set itself or they're limit points. Okay. In either case, whether they are in E or in E prime, no matter what case it is, given any epsilon, there exists there exists points P prime and Q prime that are in E that lie in the neighborhood of the epsilon over 2 neighborhood of P and the epsilon 2 neighborhood of Q, respectively. Okay. So here's a P and here's a Q. These guys are in P bar. Okay. Take an epsilon over 2 neighborhood here. Okay. Take an epsilon over 2 neighborhood. we know that there's somebody from E inside these epsilon over 2 neighborhoods. Right? There's somebody in here, and there's somebody in here. Right? Because if they're a limit point, then there's somebody in the punctured neighborhood, right? If they're not a limit point, they're in E themselves. So you could take P prime to be P, right? Right. If they're not a limit point, then they have to be in E themselves. So there's definitely somebody in E inside there, inside the neighborhood, namely themselves. Okay. Okay. So now think. The distance from P prime to Q prime. What can we say about the distance from P prime to Q prime? Actually, sorry, got it mixed up. Sorry, the distance from P to Q, sorry. If we look at the distance from P to Q, that's controlled by the distance from P to P prime plus the distance from P prime to Q prime plus the distance from Q prime to Q. Right? By the triangle inequality. Yeah? Everybody okay? Right? Okay. So, and the distance from P to P prime is epsilon over 2, right? And the distance from Q prime to Q is less than epsilon over 2. So we get that this is less than the distance from P prime to Q prime plus epsilon. Okay, so and that is controlled by the diameter of E. Right? That's controlled by this thing is controlled by the diameter of E, right? Plus epsilon. Right? Because the diameter of E is the supremum of the distances between points in E. Right? Okay, so what does that tell you? That tells you that whenever you take 2 points in E bar, right, then the distance between them is controlled by the diameter of E plus epsilon, right? So taking the supremum over all P and Q in E, we get that the diameter of E bar, the diameter of E bar is controlled by the diameter of E plus epsilon. Everybody okay? Right. Okay, so, but this is true for every epsilon, right? This is true for every epsilon, and so that means that the diameter of E bar is less than or equal to the diameter of E. Right, because you can let, this is true for every epsilon, and so you let epsilon go to 0, and then you get this result. You get that. Does that make sense? Yeah, Anne.
There, we get that the diameter of E bar
Mhm.
is less than or equal to
diameter of E plus epsilon,
Yeah.
but we have just a plane less than in the middle of that long inequality, string of inequality. So I'm wondering how we kind of recovered the equality.
Oh, okay. It's still okay. This is that thing where so this is less than or equal to that, but when you take the supremum, you might get an equal. You might get an equal sign.
Okay.
That's sort of thing.
Okay.
Yeah. Okay. Does the last part make sense? Let me just draw a picture. Here's diameter of E plus epsilon. Here's diameter of E, right? And we know that this guy is less than or equal to that guy for every epsilon, right? And then we conclude that this guy must be less than or equal to that guy, right? The point is that you know, if this guy were greater than that guy, right? If the diameter of E bar were strictly greater than the diameter of E, right? Then you would choose your epsilon, just choose an epsilon so that diameter of E plus epsilon would be lower than the diameter of epsilon bar, diameter of E bar, and that would give you a contradiction, right? We know that this guy is smaller than this guy for every epsilon, right? For every epsilon. Well, suppose that this guy is actually strictly greater than the other guy. That would lead to a contradiction, because then you could take your epsilon to be like just smaller than the difference. Take your epsilon to be smaller than the difference, and then you would get it. That would be a bad epsilon, right? Because then you'd have this epsilon, diameter of E plus epsilon is actually less than the diameter of E bar, but that contradicts this, right? We know that this is true for every epsilon. Charlotte, do you have a question?
I think I get it.
Okay. I never understood anything that my teacher said in class. So if it's not clear, go home and think about it. And if it's still not clear, then come and talk. And I just, after every class, I just went back and copied all my notes over again. And I went back to my high school, and my high school teacher said, you know, I learned everything in the library. So what is the point of us teachers? In that case? Okay. Okay. So now let's get back to the main stream of the conversation. So we've just seen that if you're Cauchy, that does not imply that you converge, but if you converge, you are definitely Cauchy. Okay. We introduced the following definition: a metric space is called complete if every Cauchy sequence converges. Okay, if every Cauchy sequence converges. So basically, if in your space Cauchy actually does imply convergent, then you're called a complete metric space. Okay, so in those metric spaces, we already showed this, right? So in a complete metric space, Cauchiness and convergent are the same thing. Okay, that's the point. That if you're Cauchy, you're convergent. If you're convergent, you're Cauchy. Okay, and this turns out to be the property of R that Q does not have. It's a complete metric space. Okay. And the theorem that we're going to prove next is following that any compact metric space is complete. And second, that RK, the Euclidean space with the standard metric, is complete. Okay, so, in particular, R itself is complete. Okay, so to do this, we're going to need the following lemma, which is that suppose you have let K sub n denote a sequence of nested compact sets in your metric space, whatever, X. Some metric space X. In a metric space X. Okay. If the diameter of the K sub n's goes to 0, then the intersection of the K sub n's consists of only one point. Then the infinite intersection consists of only one point. Okay, so you've got these compact sets, right, and they're nested, right, and the diameter goes to 0, right, and we're saying that the infinite intersection, if you intersect all of them, you're going to get one and only one point. Okay, part of this we did already. We already showed long time ago that the infinite intersection is non-empty, right? So recall we had this result that this thing is going to be non-empty. Right? If you've got nested compact sets, then the infinite intersection is going to be non-empty. So we know that it consists of some points, right? So we just have to show that it can't have more than one point. So we want to. It suffices to show that the intersection cannot have more than one point. Okay, but that's actually pretty obvious, right? Because if the infinite intersection had more than one point, then what would happen? Why does that give us a contradiction? What does that give us a contradiction with? Diameter. Right? If there's more than one point, then there's 2 points, right? Or more, of course. Yeah. But there's definitely 2 points. And in that case, the diameter couldn't go to 0, right? Because every one of these guys would contain those 2 points. Right, and then the diameter is going to be has to be greater than or equal to the distance between these 2 points. That's basically it. Yeah. So if this thing had 2 points, P and Q, then the diameter of each case of n right, would be greater than or equal to the distance between P and Q, which is greater than 0. So there's no way you could get to 0. Right, there would be this constant that you couldn't get smaller than. Okay, so that's pretty simple. Okay, so let's get to the main result here. Any compact metric space is complete. So let's do number 1 first. So proof of 1. Okay. So any compact metric space is complete. So we want to show, what do we want to show? What do we want to show? Any compact metric space is complete. In other words, what does complete mean? It means that if you're Cauchy, then you converge, right? So we want to show that every Cauchy sequence converges. Okay, so let p sub n be some Cauchy, be a Cauchy sequence in X, a compact metric space. Okay. Okay. So now consider the tails E sub n, Pn plus 1, etc. Okay. Anybody know what we're going to do? Can you guess from the lemma what's our tactic is going to be? Our strategy is going to be? We're going to want to intersect. Yeah.
Oh, take the nested E sub n, so like En and then
Yeah.
Un plus 1.
Yeah, right. These guys are nested, right? En contains En plus 1 contains, et cetera, right? But they're not compact. They're not compact. But we can make them compact. Well, we just close them. We close them, right? Why are they compact now? You have a closed set.
Was it closed and bounded set?
No.
Okay.
No. Anybody see the key word here?
Like intersection of close.
Julia?
Closed inside a compact set is.
Closed inside of a compact set is compact, yes. Right. So now they're compact. Now we've got compact nested. Right. This thing satisfies the lemma. So so the intersection of all of them, right? Consists of a single point. Right. Satisfies the lemma because right, they're nested compact sets whose diameter goes to 0. We should probably make that completely clear. Why does the diameter go to 0? Why does the diameter go to 0?
I mean, like, well, we defined it as a Cauchy sequence.
Exactly,
now.
exactly. It's Cauchy, which means that the tails, the diameter of the tails goes to 0, right? And from our previous result, the diameter of the tail is the same as the diameter of the diameter of the closure of the tail is the same as the diameter of the tail. So if the diameter of the tails goes to 0, the diameter of the closure of the tails definitely goes to 0. Right? Right, satisfies the lemma because, right, the diameter of E sub n goes to 0, right, equals the diameter of, so diameter of E sub n closure equals the diameter of E sub n, which goes to 0, and the E sub n bar are closed subsets of the compact metric space. Okay. So we know that their intersection consists of a single point. Okay, so we've got this single point, right, P, right? And do the P sub n's converge to that P? Well, we want to, make them within epsilon of P, right? That's to show convergence. Of course, we have to, given any epsilon, we can make these guys within epsilon of P. So let's do that. Say, well, look, so let me put a claim here. The Pn converge to that point. Okay. Proof. Given an epsilon, we know that there exists an n past which the diameter of E sub n bar is smaller than epsilon. Right. So if you take so what does that mean? That thus P sub n, right? The distance between P sub n and P is smaller than epsilon. Right. So for all little n, big N. Does that make sense? I hope that makes sense. Right? The diameter is smaller than epsilon, right? So the distance between any 2 points in here, is smaller than epsilon, right? Okay. Well, here are 2 points that are in there, right? This guy is in there, and this guy is in there. So for every time past big N, this is going to be true. Okay, so yeah, so there's sort of 2 parts to this theorem. One, sort of getting the point that the sequence ought to converge to, and then 2, showing that the sequence actually does converge to it. Okay. Any questions? Anybody confused? Okay, so now we just need to prove the second part, which is that Euclidean spaces are all complete. So proof of two. Proof of two, which is that RK is complete. Okay, so we have only 4 minutes left, so let me just sort of sketch this instead of me trying to drag it out. Let me sketch it. Let me sketch it for you. So you say, well, look, let P sub n be a Cauchy sequence. Okay, and we just proved that if this thing lies inside of a compact set, then we're done, right? Suffices to show that P sub n lies inside of a compact set inside Euclidean space, right? Right, because if it lies inside of that compact set, well, we know that anybody inside of a compact set, any Cauchy sequence inside of a compact set is going to converge, right? We just invoke the previous one, right? Any Cauchy sequence in the compact metric space converges, right? So if we can show that this thing, of course, RK is not compact, right? But if we can show that our sequence lies inside of a compact set, then we're good, right? Well, why should the sequence lie inside of a compact set? We're in RK, right? What do you know about compact sets in RK? Yes?
K cells are compact.
Say it again?
K cells are compact.
K cells are compact, right? So if we can show that this thing lies inside of a K cell, then we're good, right? In other words, all we have to do is show that this sequence is bounded, right? If we can show the sequence is bounded, then just choose some K cell big enough to contain it, right? And then we're done. So really all we need to do, right? So really it actually suffices to show that the P sub n is a bounded sequence. Right? Because if it's bounded, we can put it inside of a K cell, and K cells are compact. Okay. Okay. So why is it bounded? Why does it make sense that a Cauchy sequence is bounded? What does Cauchy mean? Cauchy means that the diameter goes to 0, right? So we can say, let epsilon be 1, say. We know since the limit of the diameters of the tails is 0, that there exists some time at which, or really past which, the diameter of, let me call it n naught, okay? The diameter of E sub n naught is smaller than 1. Right? There is some time, let me just say this. There is some time when when the diameter of the tail is smaller than 1. I don't need to say past which. It's kind of redundant. Okay, so what does that mean? That means that all these points, Pn naught, Pn, n naught plus 1, et cetera, are all within one point of each other, right? They're all within distance 1 of each other, right? So they're definitely bounded, right? These guys are bounded, right? And then there's only finitely many other guys, right? So there are indeed, P1, P2, up through Pn naught minus 1. There are also these guys in the sequence. But they're finite. That's a finite set. And that's bounded. Right? So you've got these finite guys who are definitely bounded. And you've got the infinite tail, but they're all within one of each other. So they're definitely bounded. Right? Just choose one point. Everybody's within one of that one point. Right? So you've got these two bounded sets, and so the union is bounded. And so the sequence is bounded inside of the K cell. So it's Cauchy sequence inside of a compact set, and you're done. Okay, that's it. See you guys next time.